Welcome to this talk. My name is Yanmao. I'm here to present a method for detecting misclassification for autonomous vehicles or autonomous systems using spatiotemporal consistency. This is a joint work between University of Arizona, Purdue University, and Virginia Tech. Well, autonomous systems, there are some examples of it, right? A thermostat can be an autonomous system. Autonomous vehicle can be an autonomous system, of course, and surveillance systems. And typically, these systems operate along a decision-making pipeline, where at the beginning we have perception. The perception is the key of this talk today. We focus on the security of perception. In particular, we are interested in those physically realizable perception attacks. Recently, some attacks were proposed. For this one, we have stop sign sticker attack to change the class of a stop sign into a yield sign. We can project an image of a person on the ground, and that get recognized by an autonomous vehicle. We can also leverage the imperfection of the camera system to inject arbitrary adversarial patterns. The attacker can also attack LiDAR systems. They can either create an existing object, remove an existing object, or change the class of an object. These perception attacks, they change the data at the source, so they are able to bypass the traditional digital defenses like crypto-based authentication. So they can be a lot more practical, more stealthy, and thus more difficult to defend against. Very recently, this is like a month ago exactly, someone, they don't like AVs. They put a cone on top of the hood of the car, and that car permanently stopped there. I mean, unless someone goes there, remove the cone, they can proceed. So now we can see how people can easily attack an autonomous vehicle. At this time, they use an actual cone. Next time, they can just project a cone or paint some cone on somewhere or put a sticker to change a truck in front of the vehicle into a cone. We're trying to solve this problem. Well, a subset of the problem, which is the misclassification problem. Of course, the attacker is trying to change the class from one class to another. And apparently, an object being correctly classified is very important for the rest of the decision making. For example, in Baidu Apollo, they have this separated procedure for different obstacle classes. Let's take a look at this example. Let's say we're on the highway, we're driving, or autonomous driving, and there's a car in front of us. Normally, we can recognize it as a car and label it as a car. In that case, it will use the vehicle prediction model for the future trajectory prediction. And then according to the prediction, the planning module would say, okay, he's running at 60 miles per hour, I'm 2, so I can keep following. Where there's an attacker comes into place and put a sticker on the back of a car, and that changes this label to a person, then what would happen is that the prediction model will switch to use the pedestrian prediction model for the future trajectory estimation. Now, that's a person cannot run 60 miles per hour even on the highway. So the planning module would, okay, I'm gonna stop, which is not good. We're trying to detect that. We're trying to detect this misclassification attack. But why don't we just use existing defenses? It turns out that the existing defenses against perception attacks are either specific to some sensing modality, like only LiDARs, GPS, IMU, or they are specific to some attack methodologies, like they can only detect, deal with adversarial patches or norm-bounded perturbations. The reason why these defenses has such a specificity is that they focus on the input of the perception. So as long as there is a change of the attack, change the attack pattern or something like that, they have to change the defense and propose a new defense. In this work, on the other hand, we focus on the output of the perception. With this, we have the advantage of first being agnostic to different attack methodologies, but we can also be agnostic to different object detection and tracking algorithms. Again, we're trying to detect misclassification attack by verifying the spatial temporal consistency of the perception result. And what do we mean by spatial temporal consistency? Let's take a look at this example. We are driving on the street, and at the first time, we can see a few objects ahead of us. We have the preceding car, we have an incoming car, we have pedestrians walking on the sidewalk, and we have a traffic sign, a speed limit sign. As we move forward at the second time frame, different object moves differently. And at the third time frame, we can even see that the pattern of different object class has a very distinguishable pattern for us to be able to classify them. In general, we want to take the output from ODT, which is object detection algorithm, which contains the spatial temporal features indicated represented by a sequence of the bounding box, as well as the class of that object. And we're trying to find out if these two sources of information is coherent to each other. If not, we are going to claim that there is an attack. Now, there are some research questions ahead of us, right? First of all, as I said, we are taking a sequence of bounding box to classify an object. Can we even do that? Do they provide enough information to do that? How do they perform, and how robust is it against adaptive attackers who, is aware of us and try to get away from this detection? To answer the first question, we use a dataset called Berkay driving dataset, and we did some statistic analysis on it, and we find out that for the first one is for cars location, they typically centered at the center of the frame. And for person, they are on two sides of the frame. And for traffic signs, you can see a pattern moving from the center to lower corners of the frame. So according to this statistic analysis, we can see that there are different patterns of different object classes we can learn from. And we propose to use a recurrent neural network to learn such pattern. As everybody has already well known that the recurrent network recurrently take the bounding box represented in x, y, w, h, which is the center coordinates and width and height of the bounding box as input, and repeatedly take that and eventually classify a sequence of bounding box into one of the classes. How does it perform? We again use the Berkay driving dataset, and which contains 5 object classes, and we are able to achieve a classification accuracy of 95%. That means a false negative rate of 5%. But what about true positive rate? In order to have that figure, we have to define our attack model first. We assume that the attacker is trying to make the car in front of us to be misclassified as a person, like this. We assume that the attacker has the white box knowledge of the object detection algorithm, and also use the adversarial machine learning techniques to generate adversarial patches. More formally, the attacker is trying to minimize the magnitude of this adversarial patch, at the same time achieve their attack goal, which is to push YOLO's classification result to be identical to the attack goal, which is the person. With this attack, we are able to achieve above 99% of detection rate. But we cannot stop here. We have to consider adaptive attackers who is aware of our defense, has a white box knowledge of that, and try to get away from our detection. More formally, they add an additional constraint to the formulation, which is that they try to push the classification result of our RNN also to be identical to a person. And with this adaptive attacker, our true positive rate or detection rate drops down to 85%. The reason why they're able to do this is that they can change the shape of the bounding box. They can also shift the bounding box so that that sequence of the bounding box is more like a human. To deal with adaptive attackers, we additionally consider contextual information, such as the ego vehicle velocity, relative velocity to the object, location information from GPS, or the position information from RMU. And with this context information, we are able to raise the true positive rate back to 99%. We also conducted real-world experiments where we mount a TV on the back of a truck, and on that TV, we display the adversarial patches, dynamic adversarial patches. Following that truck, we have a sedan with a dash cam mounted to it, mimicking the camera, and a projector as a secondary source of noise. And these are the images of the real-world attack. Due to the time limit, I'm not going to each of them. The result shows that we are able to detect most of the attack in the real world. More evaluation results can be found from the paper. To summarize, we focus on the application of autonomous vehicles. We're trying to detect misclassification attack against those systems. And the way that we do that is to use spatiotemporal consistency. We additionally consider adaptive attackers. We use contextual information to deal with them. We are able to achieve 99% of detection rate and only 5% of false negative rate. For the future, we can use more sensors. We can use a semantic segmentation result for fine-graded spatiotemporal feature. We can also try to detect object creation attacks or use attention-based neural network, not just RNN. We can also randomize the sensor configuration to create randomize. Coming back to this example, can we deal with this? My answer is yes, because it's abnormal to have a cone on a car. The spatiotemporal consistency of the cone is not consistent. It's against the normal pattern. Thank you all for coming. I'm happy to take any questions.